Welcome back to ECE 320. What I want to do here is finish up this example that we were unable to complete in the last part of today's lecture. And this example is to design a first-order low-pass filter with a bandwidth of 100 hertz and a gain of 2 and use a 1 microfarad capacitor. We can find a first-order low-pass filter from figure 15.1 in the textbook, which has R2 and C in parallel in the feedback path and an R1 in the input path feeding into our inverting terminal. We derived in class the equations or the expressions for Z sub F over Z sub I, where Z sub F is the feedback impedance, Z sub I is the input impedance. And we know from that structure that the transfer function is in fact minus Z sub F over Z sub I. Z sub I is just R1. Z sub F is the parallel combination of R2 and C. Combining those or taking Z sub F and dividing by Z sub I, we end up with our overall transfer function equaling minus R2 over R1 divided by S R sub 2C plus 1. If we substitute in values of 1 for the R's and the C's, numerical values of 1, we end up with, if we neglect the sign of minus 1, we end up with a transfer function of 1 over S plus 1. So that now the transfer function h of j omega, if we are interested in its frequency response, is 1 over j omega plus 1. We can see that the 3 dB frequency or the cutoff frequency or the break frequency is 1 radian per second. We can plug in omega equal to 0 to give us our transfer function's characteristic at DC, which gives us 1 over 1 or 1, and these particular values, a bandwidth of 1 radian per second and a DC gain of 2, are not quite what we need to satisfy our design requirement, which was to have a bandwidth of 100 hertz and a gain of 2. So let's start by trying to find a frequency scaling that will produce a bandwidth of 100 hertz versus a bandwidth of 1 radian per second. To accomplish that, we need to perform our frequency scaling. Where now we want our new frequency to be K sub F times our old frequency, where our old frequency was 1 radian per second, and our new frequency is 2 pi times 100, or 2 pi F nu, where F nu is 100 hertz. And if we take the ratio of those, K sub F is now omega nu over omega old, which now allows us to say that this is, maybe in terms of our notation that we set, our final frequency over our initial frequency. Our final frequency needs to have the same units, so let's convert it to radians per second. That's 2 pi over 100. Omega 1 was already in radians per second, and we see now that we need a K sub F of 200 pi, or that's now roughly 628.3 in terms of a numerical value for K sub F. Now we've learned how to magnitude scale and frequency scale, and we can combine those, and we need to combine those so that we can actually use the capacitor value that we wanted. Remember, we wanted to end up with a capacitor value of 1 microfarad. So we're going to use the required capacitor value, use the required cap value, and this frequency scaling, K sub F, to actually find or determine our magnitude scaling, K sub M. So we're doing it a little bit, maybe not in a direct fashion. We're sort of going We used the frequency scaling directly, or we found it in a more direct fashion. Now we are backing out the magnitude scaling indirectly from parameters that we were given in our problem. If we now look at the combination of magnitude and frequency scaling applied to the capacitor formula, then we see that the new capacitor value, which we want to be 1 microfarad, so this is now the new capacitor, is related to the old capacitor value, that's C sub 1, by our frequency and magnitude scaling, and that's now dividing the old capacitor value. This is the formula that relates our new capacitor to the old capacitor. We know C1, that we fixed to be 1 in our circuit, in our low-pass filter circuit. We have knowledge that we want to have a 1 microfarad capacitor, so we know C sub 2. We've also found K sub m right here to be 628.3. We now know 3 of the 4 parameters in that expression. We can now solve for K sub m in terms of all of the known parameter values, so that now K sub m is C1 over K sub f times, or again in the denominator, the product, K sub f times C sub 2. Again, C sub 1 was 1. K sub f was 628.3, and C sub 2 was 1 microfarad. If we plug those numbers into a calculator, we end up with K sub m being 1,591.6. We can now use that magnitude scaling to scale all of our impedance values, which are just resistors. We have R1 new. Now we kind of have to get around the 1 and 2 subscript because I had an R1 and an R2 in our original circuit. So let me call the new ones and the old ones. We have R1 new is related to R1 old by this magnitude scaling, which was 1,591.6 times, and we set R sub 1 old equal to 1. R1 new now is equal to 1,591.6 ohms. R2 will be similarly computed. R2 new is K sub m R2 old, and again that becomes 1,591.6 ohms. We're not quite finished, because if you keep track of what we've done, all we've done so far is change the magnitude of our impedance values and frequency scaled, but our original problem asked for a gain of 2, let's say in the pass band, and we started with a DC gain of 1. So we haven't yet accommodated that gain. And here is our formula, or our expression for the transfer function of that system, and you can see that the gain can be influenced by both R sub 2 and R sub 1. But what we want, so here is our gain, since we have this in time constant form, but notice R sub 2 is also going to influence our break frequency. So if we adjusted the gain via R sub 2, we would also simultaneously be throwing off our cutoff frequency that we've just calculated. So we probably don't want to do that. What we want to do is adjust the gain by adjusting R sub 1, and that won't change the cutoff frequency. Let me try to write down what we have. Presently, in our system, if we stopped right now, we have a gain of 1, since we didn't change that yet, and that's going to be influenced by the choice of R1 or R2. we saw that we can adjust R1 or R2 to in fact change the gain. But I hope that by the highlight that I just had done earlier, however, if we changed the gain by changing R2, we would also change the time constant or the cutoff frequency. So, however, R sub 2 also influences the cutoff frequency, or the time constant. Those impact each other. And for that reason, let's then use R1 to adjust the gain, because if we adjust R1, we won't change the time constant or the cutoff frequency. So we're going to use R1 to adjust the gain. And in our circuit, we derived the transfer function, and the gain was this R2 over R1, and we want that to equal 2, which now says that R1, if we solve for that, needs to be R sub 2 divided by 2. Or now we can solve for R sub 2, R sub 1, which is R sub 2 divided by 2. That's this 1,591.6 divided by 2, or that now gives us 795.8 ohms. Which means that if in our original circuit, if we make C equal to 1 microfarad, we make R sub 2 equal to 1592, and we make R sub 1 796, then we will end up with a low-pass filter that has a bandwidth of 100. It's a first-order low-pass filter. It will have a bandwidth of 100 hertz, a gain of 2, and we have actually incorporated a 1 microfarad capacitor. And that then finishes the design of that particular circuit.